Guys, this is Academic Chemistry, Chapter 4, Section 2, Part 3. So in this section, we're going to talk about J.J. Thompson and what he did to further the model of the atom to what we know today. So before we had John Dalton, and he just made everything look like little golf balls. Like he knew that there were atoms and they were really, really tiny, but he didn't think there was anything that made them up besides that he could really think of at that point. And keep in mind what John Dalton did was brilliant for that time. We just need to make it a little more modern. So J.J. Thompson comes in and he has the next step to the model. Keep in mind also that you already know the structure of the atom, so you can kind of see where this is right and where this is wrong. So J.J. Thompson is responsible for what we're going to call the Plum Pudding Model, and we're going to explain why it's called the Plum Pudding Model by going through what he did. So in 1897, which really isn't that long ago, this is 120 years ago, J.J. Thompson used a cathode ray to study matter. So let's discuss what a cathode ray is. So here is the basic structure. So you've got this tube here, so you can kind of think of like a water bottle, right? So it's just this empty vessel, and you've sucked all the air out of it, so nothing left. And you have these two metal plates. The metal plates are connected by a power source. So once you run the power source, you're going to have a positive and a negative plate. What seemed to happen, what he noticed is once you ran the power source, you have this little slit in the positive plate, then this would all glow here, and there would be a stream of glowing particles that came out. So when the power source was on, a beam shot out from one piece of the metal to the other. And since this, if we call this the first piece of metal and this the second, those are just arbitrary numbers I'm giving them. The second piece of metal has a hole in it, so that's how that beam can come through. And it's a nice clear beam because it just goes through in the location where the hole is on the second piece of metal. So we know now that the beam, the cathode ray itself, so this beam right here is called the cathode ray, that was made out of electrons, but Thompson didn't know that yet. Just keep that in mind because it's going to make a little more sense when we talk about what the beam did. A key point in this whole lesson is that opposites attract. You have to keep in mind that for the whole rest of the lesson to make sense. So J.J. Thompson knew that. You've heard it before, but for electrical charges, opposites attract. Positive goes towards negative, negative goes towards positive. So when J.J. Thompson wanted to know what this beam was made out of, he put plates on of opposite charges on either side of the ray. So we now have a positive plate up here and a negative plate up here. So when he turned the power source on, he noticed the beam went up. So if the beam went up, if the positive source is up here, if the beam goes up, that means the beam was attracted to the positive source. So because the beam is attracted to the positive plate, the beam must be negative. Okay, so now we know we have this glowing beam and it's negative charge somehow. So Thompson said, well, there has to be particles coming out of this metal. And he knew that because he changed out for different types of metal. So that way it wasn't definitely like, say he started with iron or if he started with sodium, like it wasn't one type of metal. Any type of metal he put in here did that. So that way you knew that this beam of particles was coming from the metal. And he said, well, these negatively charged particles that are coming from the metal, he named them electrons. The other thing to know is Thompson figured out the size of these really tiny electrons, and he figured out that they were so small. Like if you compared them to a hydrogen atom, they were eensy weensy, teeny weeny. So they must be subatomic or smaller than the atom particles. So that's how he knew that it came from the atom. At this point, Thompson also realized that if atoms have electrons, which would made up those cathode rays, then they must also have positively charged particles because something had to cancel out that negative charge. If each electron is a -1, it needs one something positive to cancel it out. And he called those protons. Now, he didn't really have any evidence about these protons. It just kind of makes sense. If you have no overall charge and you have, let's say, 10 negative things, you must have 10 positive things to cancel out. So whenever you have the same number of electrons and protons, the overall charge of the atom is neutral. And if you just like look around you, say touch your desk, you didn't just get electrically shocked, right? So the number of protons and electrons have to be equal because the atom is a neutral thing. So when Thomson imagined the atom, it only made sense to him to assume that the protons and electrons were evenly spread around the atom with mostly empty space. So this is a fairly good representation, but imagine them just even spread even more apart. So you just have mostly nothing, and then just every once in a while you'll have that positive and negative charge that are just hanging out inside the atom. And there was no reason for him to think that it didn't have that structure inside. That just kind of, oh, if they're in there, they're just sporadically around. So this model is called the plum pudding model because it literally, in his mind, when he described it to people, it kind of sounded like pudding with little bits of plum inside. Apparently that is a dish that some people eat. I've never seen it, plum pudding, so I always think of this as like the chocolate chip cookie model because personally I much prefer thinking about chocolate chip cookies than anything to do with plums, but it's good to know the actual name. So that's it for the end of this section. In the next section, we're going to talk about why the plum pudding model doesn't actually pan out when we talk about the modern atomic theory.